Right, last time we talked about homology. It's formalized as a sequence of functors right, where we had some subcategory of pairs of topological spaces, and we ended up in abelian groups. Together with natural transformations from Hn, well, might as well put an n, Hn xa to Hn minus 1, a empty set, satisfying what are known as the Eilenberg-Steenrod axioms. Homotopy, excision, additivity, exactness, and dimension. Right, so homotopy equivalent maps should give you the same induced maps between abelian groups. Excision should give you an isomorphism. Additivity is when you have disjoint unions. Exactness is you get a long exact sequence. And dimension says that if you have a space that's only a single point, then the homology should be concentrated in degree 0. Right? And we talked about how if you have everything except that last one, so a generalized or extraordinary homology theory is one that satisfies all but dimension. Right, and we saw one example, which is Bordism homology.
Does a generalized homology theory necessarily not satisfy dimension?
No, you could consider homology as a generalized homology theory. It's just you don't impose that. Bordism homology, so this sequence looks like this, and this one is nice because it's very similar to homology. You just replace singular simplices with singular manifolds. So you use manifolds with boundary as your chains. But there are many others. K-theory, which you might have heard of, is another generalized homology theory. And that one is, it's periodic. And so it doesn't have, dimension fails drastically. It doesn't only not have groups with negative degree, it has groups with every degree. Okay, so that was last time. Questions on last time?
What do you mean every degree?
So for example, you talk about k minus 1 of x and k 27 of x. So for every, it's not just the natural numbers, it's every integer, n. More questions? Right, so I said last time that this is really beautiful and you should all read about this. So Tom did compute the homology groups. Well, he computed things tensored with Q in the oriented case. But he did characterize one or two topological manifolds bordant. And it's in terms of something called characteristic classes, which also ties in with K-theory. And it's a beautiful topic that we used to have a course about, and sadly do not anymore. But Milnor has a wonderful book on it. I suggest reading Milnor. OK. So today, the first thing we want to do is relate PI1 and H1. Right, so way back when we were defining homology, we talked about how the first homology group is just the abelianization of the fundamental group. So now we want to prove that. Okay. So the fundamental observation is that if you have a map from 0, 1 into a space, then you can think of this as a path or a singular one simplex. And as a path, you'll get a representative of an element of the fundamental group. So it represents an element of pi1 if f of 0 is equal to f of 1. And that's the same in terms of singular one simplex of being a cycle. If and only if f is a cycle in the first singular chain complex group. So we can interpret it, meaning a loop, as a representative of a class either in pi1 of x with base point where it starts, or h1 of x. Okay, and so the theorem is that this identification induces a map, call it little h, from pi1 of x to h1 of x. If x, well, let's put in the base point. If x is path connected, then h is surjective. And the null space is equal to the commutator subgroup. So H induces an isomorphism between the quotient, which is the abelianization of pi1 and h1. Right. As an aside, H is a natural transformation. Between the functors pi1 and h1. Okay, so we have really we have an ambiguity here. We have a loop. We can think of it as being an element over here or an element over here. So the first thing we're going to show is that this ambiguity actually gives you a map from here to here. So these are equivalence classes of loops. So we're going to see that equivalent loops give you equivalent homology classes. And so you get a map. And then we're going to show that it's surjective and identify the null space. OK? Questions so far? So let's just be clear on our notation. We'll use this symbol for path homotopy. Remember, a path homotopy is a homotopy that fixes the endpoints. And we'll use this symbol for homotopy equivalent. No, for homologous. OK, so this will mean that they represent the same element in the fundamental group, and this will mean that they represent the same element in the homology group. OK, so the first thing to notice is that if f is a constant loop at x naught, then f is homologous to 0. Right? F is trivial in homology. OK, so how do we show that something is trivial in homology? We show that it is a boundary. So I want to give you a 2-simplex whose boundary is f. So, well, f is a pretty trivial map. So take a pretty trivial 2-simplex. Let sigma have image f of 0. Right, so just take the whole 2-simplex and map it to that point. Then the boundary of sigma is going to be f minus f plus f, which is f. OK. So second thing to note is that if f are path homotopic loops based at x naught, then they are homologous. So indeed, take a path homotopy between them, and then what you want to do is divide the square into simplices. Well, maybe instead of putting arrows, I'll just label. Well, I'll put arrows. 0, 0, 1, 0, 1, and then these arrows that way, so it's pointing there and there, right? So you're doing f on one end, you're doing g on the other end, and the sides are constant maps because it's a path homotopy between them. Right? So take the boundary of sigma 1 plus sigma 2, and you get f minus g plus, well, I guess you get g minus f. Plus a constant path minus a constant path. So since the constant paths are trivial in homology, that means that in homology, F and G are equivalent.
Can you explain again what your square drawing remember?
Yeah, so take the square, where you're doing F on one end, G on the other, and these ends are constant paths. Right? Split this into two simplices. Right? Then modulo getting the orientations right. When you take the boundary, you're going to get the bottom minus the top, and one end minus the other end. Right? And one of them is going to be F, one of them is going to be G, and then you have these constant guys. So changing and getting the orientations right is going to tell you whether you get G minus F or F minus G. But in any case, you get F and G are equivalent in homology. Right. Yes?
I'm a little confused why you have that arrow at the top.
Yeah, so if we label the vertices V0, V1, V2, right, then this oriented two-simplex should be pointing always towards the larger number, right? But then remember that when we were studying this a million years ago, it was confusing that this one, to get the orientation right, you have to be looking at it from the other side. Right, so if these arrows are all pointing that way, and then you flip this around, then the arrows should be pointing to, oh, I think I have this arrow. Oh, no, I think it's fine. Dun, dun, yeah. So this is the larger arrow. But in any case, don't worry about the orientations. The point is that you have F on one side, G on the other, and these two simplices. And if you take the boundary of this plus this, or maybe minus this if you want to change the orientation, then you'll end up with F minus G.
So despite the direction of that arrow, F still travels as usual from 0 to 1.
That's right, from 0 to 1. Yes, the reason I get a minus is because the arrow is pointing the opposite way.
Okay.
But you know, if you were to orient these differently, that's okay. You'll just get the same thing up to a sign. Okay, so that tells us that we have a well-defined map between loops and homology classes. Because if two loops represent the same element of PI1, then you get the same element of H1. Right? We want to know that it's a homomorphism. So the third thing to notice is that if you have two loops and you take the concatenation, then this is homologous to F plus G. Right? So this is the product in the fundamental group, or this induces the product in the fundamental group, and this induces the product in the homology group, and we want to see that we get the same thing. Right? So again, we just have to draw the appropriate two-simplex. In this case, just take this two-simplex. So let's say this V0, V1, V2, which means that the arrows are all pointing like that. And I want to do F then G, so I want to do here F then G, and I'll just have F on this side, G on that side. So if this is the two-simplex you're looking at, then the boundary of sigma is F plus G minus F dot G. Okay, so this tells us we have a well-defined homomorphism from PI1 XX naught to H1 of X. It's an easy consequence that F bar is homotopic to minus F, right? So the inverse in the fundamental group gets sent to the inverse in the homology group, right? Just because if I do the concatenation here, this is path homotopic to a constant path, and this is homologous to f plus f bar, and this is homologous to 0. All right, but we really don't need to check that. All we need is that we have a well-defined homomorphism. Okay, so let's check that it is surjective.
Wait, sorry, can you say what the homomorphism is?
Yes, given a class here, pick a representative, and take that representative viewed as a one simplex.
Okay.
Yeah. I'll mention an alternate description in a moment, but it's really just that. Okay, so let's check that H is surjective. Right, assuming that X is path connected. So, so given an element of H1X, pick a representative, which we can write as a finite sum of singular one simplices. Right, or remember this is just the interval. And this has the property, of course, that boundary is equal to 0 because it represents a homology class, and this boundary is the sum of nj, sigma j of 1 minus sigma j of 0. So if we let S be the set of endpoints of the sigma j's, right, so, well, I guess distinct. So just consider all of these endpoints, and for each endpoint, so of course, what do we want to do? We want to have this be in the image of the fundamental group. That means we want to have a bunch of loops based at x0, which reinterpreted as elements of the homology group give us this element. Right? So we have these paths. We want to convert them into loops. So for each endpoint in S, pick a path with starting at x0 and, of course, ending at that point. Right? The sum nj sigma j of 1 minus sigma j of 0 we can write as, say, m sub p of p. So m sub p is just the sum of all of the nj's, all of the coefficients that a particular point p has in this sum. And because this is 0, then we know that the individual MPs are 0. Okay? So consider so just take, okay, for each j, take eta j to be beta sigma j of 0. No, probably want 1, right? Well, I'll finish right. Sigma j dot beta sigma j of 0. So you're going to start at x naught. That's going to take you to sigma j of 0. Then you're going to do sigma j, gets you to sigma j of 1, and then you're going to do beta sigma j of 1 inverse, and that gets you back to x0. All right, so this is a loop based at x naught. So now if we take h of eta 1 to the n1 times eta 2 to the n2 times dot, 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 until you get to, I should have given this. So j goes from 1 to capital L, well, to L. Eta L to the n sub L. All right, so this is a loop based at x naught. So it represents an element of the fundamental group. Yeah, let's take the corresponding element of the fundamental group based at x naught. All right, I can hit that with h, and I'm going to get an element of the homology group. And that's going to be n1 eta 1 plus n2 eta 2 nl eta l. And that's ni, and then each of these etas becomes minus beta j of, beta sigma j of 1 plus sigma j, beta I. Sigma I plus beta sigma I of 0. And that is the sum ni sigma I plus the sum ni beta sigma I of 0 minus beta sigma I of 1. That's the sum ni sigma I plus the sum, actually minus, but whatever, mp times p. Well, times beta p. Yes?
Is the concatenation defining eta j written backwards?
Entirely possible.
Because this is the confusing thing where when we write a concatenation, the first path you go across is the one that's first, as opposed, the one on the left.
Yeah, and
function composition.
In that case, I wrote it exactly backwards. Thank you. There we go. Okay, but of course that doesn't change anything over here because homology is abelian. Yes?
I have a question about this word.
Sure.
Where is the homologous thing coming from in the last line?
Here?
On the left. There.
Here.
Yeah.
Yeah, so so if you like, this is homologous there and this is homologous there.
Oh, okay, okay.
Yeah. Okay. So we get this, and of course the MPs are all equal to 0. So this is just 0, and so this is equal to L, to lambda. Yes?
Sorry, what's NP?
MP is just the coefficient. So this sum is over the endpoints, right? Each endpoint occurs at least twice, but it might occur more times. And so it gets coefficient nj, possibly with the sign. So take the fix for each point, p, you get some total coefficient m sub p. Due to the nj's with their signs and whatever. So it's just whatever this sum, every time p occurs, you put those two coefficients together and get mp. Okay? So it's surjective. So all we did was we started with a representative of the homology class. It's a sum of singular one simplicities, and we just turn each of those into a loop. And that gives us an element, a representative of an element of the fundamental group. And we saw that h of that element is the one we started with. Okay? Right, so it's a very natural thing to do. I see a lot of blank faces. Why doesn't this seem like what else would you do, right?
I think I understand what you're saying you're doing.
Uh-huh.
I think in this second to last board you've written on, I'm kind of lost as to why that's
Okay,
what
so
you're saying it is.
okay. Okay, so this
I trust you.
well, the wonderful thing about math is that it doesn't come down to trust, right? It's okay. So we're just turning this path to a loop, right? And we're turning it to a loop by connecting it to x naught at both endpoints. Right? So all we did was we fixed path. Right, so if you like, here's x. Here's our base point x naught. And here we have sigma 1. Here we have sigma 2. So all we're doing is we're saying, OK, well, and of course there has to be, since we ended up with a cycle, then they actually have to be connected, right? So there are more paths connecting the endpoints. Right? But all we're doing is we're saying, OK, for this point, fix a path here. Right? So this would be beta sigma 1, 0. And for this point, fix a path here, beta sigma 2 of 0. And use these paths to turn each of these segments into loops based at x naught. Right? And then you can put those together and you have an element of the fundamental group. Okay? Yes?
I have two questions.
Yes.
One, is the reason we then take those loops to the power of n1, so it will come out nice in the end?
Oh, well, since we have a homomorphism, if you're doing, where is it here? If you're doing if you're adding sigma j to itself nj times, right, then what you should be doing in the fundamental group is concatenating eta 1 to itself n1 times, right? And that gets written as a power.
Okay. And also, I don't mean to be pedantic, but I'm checking my understanding. Strictly speaking, h of this class gives us
A class. That's right. Okay. Yeah. Yeah, so you could put brackets around each of these. Right, and then this bracket corresponds to the fundamental group, and this bracket corresponds to H1. Yes, thank you. More questions? Is it more clear now?
So why do you need MP equals to 0? I think the path between beta sigma 1, sigma I 0 and beta sigma I 1 minus the 0 homologous, right?
That's right. It's just a way of seeing that they're zero homologous. I mean, the point is that here you have the path beta sigma I 0, but it occurs the same way that sigma I 0 occurred in this sum. And since they all canceled out here, they have to all cancel out here. Question? Wonderful. So next, the kernel. So let's say we have so it's the same as saying that gamma is homologous to 0. Want to show that gamma is a product of commutators. Well, let's say it's a product of commutators. Okay, so before we do that, yes?
Sorry, why are those the same, that if h of class of gamma is 0, then gamma is homologous to 0?
Yeah, so H takes fundamental class elements of the fundamental group to elements of the homology group, right? So this being equal to 0 says that the image is homologous to 0. Right? The image is the homology class of 0. Right? So now the way this map works is pick a representative of this and view it as a representative of the homology group, right? Of a class in the homology group. So if that class is the same class as 0 in the homology group, that's the same as saying that representative is homologous to 0. Right? Okay, so before we do this, we should pause and think about how do we recognize a product of commutators. All right, so here's an easy lemma from algebra. Let's say that G is a group. If W is a word in G in which for any element in G, the exponents of G in W add up to 0, then G is in the commutator subgroup. So what I mean is, so of course, obviously, if you have a commutator, then the exponents of A add up to 0, and the exponents of B add up to 0, right? But also, if you were to have A squared, B cubed, C to the 4th, A minus 1, B minus 2, A minus 1, B minus 1, C minus 4, right, then that might not be as obviously a product of commutators, but because if you look at any element, the exponents add up to 0, the lemma says that that is an element of the commutator subgroup.
Do you mean to say W is in?
That's what I mean to say, thank you. All right, so this word is an element of the commutator subgroup. Right, and the proof is actually amazingly easy. Just consider the projection from G to the quotient. Right, so we know that the kernel of this projection is the commutator subgroup. Right, so to show that something is in the commutator subgroup, it's enough to show that this projection kills it. Right? Okay, but this projection maps into an abelian group. Right? So in this group, you're allowed to commute elements all you like. So map into here, and then put all of the A's together, put all of the B's together, put all of the C's together, and they all cancel out. Right? So consider this. W is obviously in the kernel. since this quotient group is abelian.
Maybe this is obvious, but is the converse of the lemma true? Like if you're in the commutator subgroup, does that mean that the exponents will add to
Yes, so to see that, since it's true for one commutator, then it's going to be true for products of commutators, right? Because it's true one commutator at a time. Okay. Okay, so with that lemma in our pocket, let's check this. So we have gamma homologous to 0. We want to see that gamma is an element of the commutator subgroup of the fundamental group. Right? So gamma homologous to 0 tells us that there is a finite sum sigma j now 2 simplices such that the boundary of this sum is equal to gamma. Right, that's what it means to be homologous to 0. Right, and of course, the boundary map is like that. And let's say that the boundary is lambda j plus mu j plus nu j. Okay, so let's draw a picture. Let's say that we have, that one is each sigma j, so it has lambda j, mu j, and nu j. And then we have x naught over here somewhere. So, of course, we want to connect the endpoints to x naught. So we're going to introduce a path, and a path. Let's go. Right, so this is going to be beta of mu j of 0. This would be beta of lambda j of 0, and this would be beta of mu j of 0. So that is, let S be the distinct let me remember if I want points or paths. Distinct one simplices. In the list, lambda j, mu j, nu j. Okay, and for each distinct base point, of a one simplex P, fix a path beta P from x0 to P, right, just like before. Okay, so here is the two simplex, and we're just picking paths from x0 to connect. Can I help you read something? For each distinct base point of a one simplex. Endpoint, I guess. Thank you.
What's the word at the top of the?
Fix.
Fix.
Fix, yes. Okay, great. So for each theta in S, let m theta denote the coefficient of theta in the sum right, which we know is equal to 0. So this sum being this sum. Okay, so we know that this boundary adds up to gamma. So gamma has to be in this sum somewhere, right? Because this adds up to gamma. So what we have is that m theta is equal to 0 if theta is not equal to gamma, and 1 if theta is equal to gamma. Okay, now for each for each simplex, the 3 loops beta lambda j 0, lambda j, beta lambda j of 1 inverse, beta mu j of 0, mu j, beta mu j of 1 inverse, and beta nu j of 0, nu j, beta nu j of 1 inverse. Okay, have concatenation homotopic to a constant loop. Right, because when you concatenate them, you basically just get the sigma j, and sigma j is contractible. Yes?
So what do you mean when you say m sub o is 0 if o is not gamma and 1 if o is gamma?
Theta, but m sub theta
Oh,
is,
that's a theta.
yeah. So in this sum, we know that everything cancels out except gamma.
Right, but couldn't gamma be made up of multiple things in S?
Well, we could do 2 things. You could either put all of those things together to form gamma and think of gamma as one of these elements, or we could just, for simplicity, assume that it is one of these elements.
Okay.
So let's just say that gamma is one of these elements is supposed to be a sum for notational convenience, if nothing else.
What would gamma look like in the diagram?
Say that this one, for a particular sigma j, this one is gamma. For gamma, the only difference is that you don't need to add these paths because you know that it's starting and ending in x naught. Because gamma is a loop. But equivalent, you could just be adding the constant path. That'd be fine. Okay. So we formed a loop. Eta 1 to the n1 concatenated to eta L and L concatenated with gamma inverse. So these etas we form just like we did before, just putting these guys together. So this we know is homotopic. Yeah, homotopic to a constant path. Hold on a second. Okay, so yes, so we get gamma inverse because for every 2 simplex, when you concatenate these 3, it cancels out. So here, yes?
Is eta the concatenation of each of these for each?
Yes, for each sigma j, yeah. So yeah, eta, each eta j is what you get, is obtained from the boundary of sigma j.
Is it homotopic or homologous?
Homologous. Okay, so we have this on the one hand. On the other hand, if we write out each eta j in terms of the loops in star, then for each theta in S, the factor beta, the appropriate beta times theta times the appropriate beta inverse. Well, I mean, we could say theta of 0, theta of 1 appears with exponents summing up to m theta. Okay, but we know that m theta is equal to 0 if theta is not equal to gamma, 1 if theta is equal to gamma, but since we put gamma inverse, then those also cancel. Right? So by the lemma, gamma inverse is in the commutator subgroup, or the class represented by gamma inverse is in the commutator subgroup. And hence so is gamma. Okay, so what this ended up saying was that the difference between being 0 in the homology group and being 0 in the fundamental group is just the lack of commutativity in the fundamental group. Yes?
Did we prove, so we just proved that the kernel is a subset of the commutator subgroup? Did we prove that the commutator subgroup is exactly the kernel?
That's a fair point. It follows from the lemma that everything in the commutator subgroup is, in fact, even without the lemma, the commutator subgroup is 0 if you map into an abelian group, right? So since homology is abelian, it's automatic that the kernel lies, the commutator subgroup lies in the kernel.
Wait, can you say that again?
Yeah, in fact, it's a fair point. I really should have written that. So pi1, pi1. No, so we've just shown that the kernel is in the commutator subgroup. On the other hand, since H1 of x is abelian, and H is a homomorphism, the commutator subgroup is automatically inside the kernel of H. Right. Because if you're allowed to commute things, then anything in the commutator is the identity. Any commutator is the identity. So there's a nice way of thinking about the this map, or another way of describing it. So remark. You can also think of pi1 of x naught as homotopy classes of loops, right, based loops. So what you can do is if you give me a map from S1 to X, right, then what I can do is send this to the homology class of, what did we call it? Gamma 1 maybe? So here gamma 1 is the generator, gamma 1 in pi1 of x naught, which is the integers, a generator, or let's just say the loop that goes around once counterclockwise. Right, so you'll recall that the fundamental group of the circle, is the integers, right? And it's just the winding number of a loop, right? So we have a loop that goes around once counterclockwise, and that is our positive generator. So what you can do is, sorry, I meant to say in homology, which is still the integers. and it's still this loop. So this is the fundamental class of the circle, right? So we proved that every orientable manifold has a fundamental class, right? So take the fundamental class of the circle, take any map from the circle to X, and you get an induced map in homology. So push this class forward by the induced map. That gives you a homology class in X. Right? That's the map that we've been studying. Right? Because remember, what the induced map in homology is at the level of a simplex is just take the singular one simplex that was mapping to the circle and then compose it with F to get a singular one simplex in X. Right? Well, that just says take your loop, and instead of looking at it as a loop in X, view it as a singular one simplex in X. Okay, so this is the same map. It's a different description of H, but you see that it's just the induced map in homology. A similar remark. Just back to the Bordism homology. This also has a natural transformation to homology, to singular homology. Right, namely, if you have remember, this is represented by a map from an oriented manifold into X. Right? So all you have to do, so since M is oriented, so it has a fundamental class in Hn of M. Right? And M is an oriented N manifold. So it has a fundamental class here. So all you need to do is take this and send it to the induced map in homology of that class. And that'll give you an element of homology there. Right? And that defines a natural transformation between these. Right? So very much like for the circle. This is actually where everything started with Bordism homology. Steenrod asked, which homology classes can you represent with a manifold, right? So this is what he meant. This is what's called Steenrod representable, is which homology classes can you write as the image of a fundamental class of a manifold, right? And so to answer the question, it's useful to use this natural transformation. And the answer is, well, it depends on the odd torsion. So even torsion is fine. Things that aren't torsion is fine, but odd torsion you have to watch out. Okay, so any questions on relation between H1 and PI1? Okay, so the next thing we want to prove is the Jordan curve theorem. All right, so let me remind you that a simple closed curve in R2 is the image of an injective continuous map from S1. Right. So it's just a loop that doesn't intersect itself. Right. So the Jordan curve theorem says that every simple closed curve divides R2 into an inside and an outside. Right, or more formally, the complement of a simple closed curve, it has two connected components, both of which have the curve as their boundary. So as you would expect, it's a sort of theorem that it was very hard for people to realize that there was a theorem to be proven. So Jordan So this is Camille Jordan, right, the French mathematician from the early 20th century, who's famous for his books on algebra that popularized Galois theory. He's actually the same guy who came up with the notion of homotopy as a relation. And he came up with this theorem when he was writing a textbook on analysis, where he introduced the length of a path and a function of bounded variation. So he was very modern in including topology in an analysis textbook. And one of the things he needed was this theorem. The theorem, his proof fell into disrepute because Oswald Veblen, an American mathematician, wrote his PhD thesis on axioms for geometry. And he claimed that this proof was wrong. And he claimed that it was wrong because it didn't, because it assumed the case of polygons, and that his proof was right. For a long time, people just cited Veblen and saying, well, Jordan gave an incorrect proof of this in 1877, but the correct proof was Veblen in 1905. But recently, people have gone back and reread Jordan's textbook and said that actually that proof is fine. There's nothing wrong with that proof. And in particular, the case of polygons is very easy. Let me tell you the idea for the case of polygons. If you have a polygon with finitely many sides, what you want to do is pick an axis that is not parallel to any one of the sides. So say that line. And then on every one of this line, at every point, you can associate just how many times have you crossed the simple closed curve, right? And so, right, so here you haven't crossed at all. Here you've crossed once. Here you've crossed twice. And it turns out that you can connect all points with an even number, and you can connect all points that have crossed an odd number of times, but you can't connect even with odd without crossing the curve. And so those are your two connected components. So you can take it as an exercise. There are apparently high school textbooks that leave that as an exercise to show that that does give you two connected components of the plane with the curve as their boundary. Right? Yes?
So I thought the Jordan curve theorem, and in particular the hard part, wasn't just that the curve divides R2 into two connected components, but that then one of those connected, those two connected components are homeomorphic to the inside and outside of a circle.
Right, that's a separate theorem. That's due to Schoenflies.
Ah, okay.
So he showed that, moreover, from this statement, there is a homeomorphism of R2 that takes the curve, I don't know if I gave it a name, the curve, to the unit circle. So yeah, this, so whereas the Jordan curve theorem generalizes to arbitrary dimension, and we'll soon prove it for arbitrary dimension, the Schoenflies theorem does not generalize to higher dimension. But it says in R2 that not only are you dividing the two pieces, but the inside is homeomorphic to the inside of the disk, and the outside is homeomorphic to the outside of the disk. Right? So you can homeomorph the entire plane until you've taken the curve to the circle. Yes?
Is this related to the Riemann mapping theorem?
Sure. I don't think it's a particular case, though. I think the Riemann mapping theorem is more like, if things are analytical, then you can do this analytically. Okay. Yes?
So when you see that the Schoenflies theorem fails in higher dimensions,
Yes.
what particularly is the generalization there? Because you end up with tricky things where, like for instance, if you have a simple closed surface, whatever one might, define that to be, it's not necessarily, presumably a compact, two-manifold. It's not necessarily simply connected. Is that why you're saying it fails, or are you saying that even if the surface is homeomorphic to the end sphere, then that doesn't necessarily extend to the entire space? Right.
So what happens is, if you look at, say, the image of S2 in R3, right? So the next case up, it can happen that that the two pieces are not even simply connected. Right? Neither of the pieces are simply connected.
Okay.
But it turns out that what goes wrong, indeed, is a lack of regularity. So if you have a mapping of S2 into R3, and you know that the two connected components are manifolds, then there is a homeomorphism of R3 to itself that takes it to the unit sphere. Yeah.
And presumably there's some sort of smoothness or differentiability on the surface itself that you could also use to get that.
Well, it's really a function of the map. So what you need is for the map to be flat, is the technical condition you need. But
okay,
let's not worry about that. So the counterexample to the Schoenflies theorem in 3 dimensions was done by James Alexander, who came up with what's called the Alexander Horn sphere, which is in the textbook. It's an interesting counterexample to things, but I'm not going to bother constructing it in class, so I recommend reading about it in the textbook. But yeah, it's a counterexample to Schoenflies in 1 dimension larger. Alexander was also an American mathematician. He worked with Veblen. They were both members of the Institute for Advanced Studies as soon as it got open, for example. But Alexander, what's fun about him is that he was an avid mountaineer. And so, there were places in the Alps where he was the first person to ever climb, whatever. And so what he would do in Fine Hall is he would always leave the window of his office open in case he wanted to arrive by the window. And he would just climb up the side of Fine Hall and enter his office through his window. Also, apparently, he had a secretary, and they had a key phrase. So if she ever said, yes, of course, Professor Alexander is in, and he'd be happy to see you, that was code for him to jump out the window and climb down the side of Fine Hall to escape whoever was coming to see him. Yeah. Yeah, so. Well, I don't want to start the proof and then stop, so let's just stop there. And we'll prove the Jordan curve theorem next time.